Hey there guys, this is the 2019 Edexcel A-Level Maths Paper 3-2, which is the mechanics part of Paper 3. Let's do this. The 1 at time t seconds, where t is greater than or equal to 0, a particle p moves so that its velocity, v meters per second, is given by v is 6ti minus 5t to the 3 halves j. At time t equals 0, the position vector of the particle is minus 20i and 20j. Part A. Find the acceleration of p when t is 4. Alright. So, acceleration is the derivative of velocity. So here, A is going to be 6i minus 3 halves times 5, so 15 halves t to the 1 half. J. So then A, when t is 4, is 6i minus 15 halves times the square root of 4, so minus 15j. Okay, and then part B, find the position vector of B when t is 4. Alright. So, it's important to remember with this one, P does not start at the origin. P starts at minus 20i add 20j. So, in general, the displacement S, or we could use R, either one is fine. So that's going to be minus 20i add 20j add the integral of velocity, that gives us displacement. So, that's going to give us minus 20i add 20j now 6t integrates to 3t squared, so we have 3t squared I, and then minus 5t to the 3 halves integrates to minus 2t to the 5 halves j. So, altogether, the position vector is minus 20 add 3t squared I add 20 minus 2t to the 5 halves. So finally, S when t is 4 is gonna be, now then, minus 20 add 3 times 4 squared, so that's minus 20 add 48, so that's 28i. Add, now 4 to the 5 halves is 2 to the power 5, which is 32. Then times that by 2, we get 64. So we have 20 minus 64j, so that's minus 44j. Number 2, a particle P is moving with constant acceleration 2i minus 3j meters per second squared. When t is 0, the particle is at A and moving with velocity minus I at 4j meters per second. At time t is capital T, the particle is moving with direction 3i minus 4j. Part A, find the value of t. Alright, so, it's quite tricky. So, what do we know? Well, we know that the initial velocity u is minus I add 4j. Now, we don't know the final velocity. All that we know is the direction it's moving in. So, what we can say, I guess, is that v is a scalar, so let's say k, lots of 3i minus 4j so again we know where it's moving, but we don't know the size of the vector, and we also know that A is 2i minus 3j. Alright, so this is a job for Suvat. So the one we are going to use is V is U add A T. So alright, well I guess we also know that T is capital T. Alright, so we know then that K times 3i minus 4j is equal to U. So minus I add 4j add a times t. So that's going to be add 2ti minus 3tj. Alright, so on the right we have 2t minus 1i add 4 minus 3tj. Alright, now remember we don't know the actual final velocity. What we do know though is that the I and j components are in the ratio 3 to minus 4. So that means then we would need minus 4 lots of the I component and that would be equal to 3 lots of the j component. Alright, now if we expand, we're going to get minus 8t add 4 is equal to 12 minus 9t. So add 9t and we get t and subtract 4 we get t is 8. And that's seconds. B at time t is 4, B is at point B. Part B, find the distance A, B. Alright, so this time then we want to work out displacement after 4 seconds. So this time we are going to use S is ut add 1/2 at squared. So, and also this time we know t is 4. Alright, so S is ut, so minus 4i and 16j and then add 1/2 at squared. So 4 squared is 16, half of that is 8, so we are adding 8a. So that's going to give us add 16i minus 24j. So, altogether, we have 12 I, and then minus 8j. Alright, so that tells us how to get from A to B. What we want is the distance, so the length AB is the modulus of S. So the square root of 12 squared and 8 squared. Doesn't matter that it's a minus 8 because we're squaring it. Alright, so that gives us a root 208, which would be a fine answer, except we also need to put meters, or to one decimal, that's 14.4 meters. The two blocks A and B of mass 2m and 3m respectively are attached to the ends of a light string. Initially, A is held at rest on a fixed inclined plane. The plane is at an angle alpha to the horizontal, where tan alpha is 5/12. The string runs over a small, smooth pulley fixed at the top of the plane. The part of string between A and B is parallel to a line of greatest slope of the plane, so that just means it runs straight up the plane, not diagonally across. Block B hangs freely under B. The coefficient of friction between A and the plane is 2/3. Blocks are released from rest with the string taut and A moves up the slope. Immediately after the blocks are released, the tension in the string is T. The blocks are measured as particles and the string as inextensible. Part A, show that T is 12 mg over 5. 8 marks. Good times. Alright, so I'm gonna start with what we know about alpha. So we know tan alpha is 5/12. So if that means there is a right-angled triangle with an angle alpha where the opposite is 5 and the adjacent is 12. Now, using Pythagoras, we can get the hypotenuse as the square root of 12 squared and 5 squared, which is a root 169, which is 13. So, from that, we can get sine alpha and cos alpha. So, sine alpha is 5/13. and cos alpha is 12 thirteenths. Alright, so we're going to need those for the forces acting in this system. Alright, so now then to the diagram. So in terms of A, tension is acting up the slope. In terms of B, tension is acting up the rope. Alright, now let's do A. So, A has a mass of 2m, which means it has a weight acting downwards of 2mg. Now, it also, or that weight has a component perpendicular to the slope like that, and also we have component acting down the slope. Now, this angle at the top of the triangle is alpha. So the perpendicular force is going to be cos alpha times the hypotenuse. So that's 2mg cos alpha. Now remember, we know cos alpha is 12 thirteenths, so we have 2mg times 12 thirteenths, that's 24 mg over 13. And then the parallel force is sine alpha times the hypotenuse. Now, sine alpha was 5 thirteenths, so here we have 2mg times 5 thirteenths, so that's 10 mg over 13. Now, we also have the normal reaction, so that's working perpendicularly upwards. So, that's the only force acting in that direction, so that's just the same as 24 mg over 13. Alright, now one final thing. At A we have friction, so that's mu times the normal reaction, so that's 2/3 times 24 mg over 13, so that's 16 mg over 13. Alright, so there is the complete picture at A. Now, what can we do from that? Well, we know that force is mass times acceleration. Now, at A, we have tension pulling us up, and then we have two forces trying to pull us down. So we have friction and the parallel part of the weight. So we can say that the force is tension minus friction, so 16 mg over 13, and minus 10 mg over 13, so that's minus 26 mg over 13. We know that that is the mass times acceleration, so 2ma. Alright, now we're going to do B, which is a lot easier. So at B, we got tension pulling us up, but weight is winning, and pulling us down, so that's 3mg. Alright. Now, let's first of all rewrite A. So 26 mg over 13 is just 2 mg. Alright, so then at A, B, we know that weight is winning. So 3mg minus T is equal to 3ma. Alright, simultaneous equations. So, if we turn each of these into a form with 6ma, we're going to get 3t minus 6mg is equal to 6ma. And 6mg minus 2t is equal to 6ma. Alright, now we need to get rid of the a's. So let's do the top minus the bottom. So 3t minus 2t is 5t. And then minus 6mg minus 6mg is minus 12mg. G, and we get 0 on the right. Add 12 mg, divide by 5. T is 12 mg over 5. Boom. After B reaches the ground, A continues to move up the slope until it comes to a rest. But B, determine whether A will remain at rest. Carefully justifying your answer. Alright. So, when A is no longer being pulled up, what's trying to pull it down? It's the component of your weight. So, that's the 10 mg over 13. Now, what's stopping it from falling back down? It's friction, which was 16 mg over 13. Now, 16 mg over 13 which is the friction, is greater than the force trying to pull it down. Therefore, it will remain at rest. C. Suggest 2 refinements to make the model more reliable. So, there's loads. Take into account the dimensions of the blocks, air resistance, the mass of the string, friction on the pulley, air resistance, anything like that. 4. So we have a ramp AB of length 8 meters and mass 20 kilograms, which is resting in equilibrium with its end A on rough horizontal ground. The ramp rests on a smooth, solid, cylindrical drum, which has its axis at the same horizontal level as A. The point of contact between the ramp and the drum is C, where AC is 5 meters. The ramp is resting in a vertical plane perpendicular to the axis of the drum at an angle of theta to the horizontal, where tan theta is 7/24. The ramp is modelled as a uniform rod. Part A. Explain why the reaction from the drum is only acting in a perpendicular direction to the ramp. Alright, so that is because the drum is being modelled as smooth, which means there's no friction between the ramp and the drum, so the only force acting on the ramp from the drum is a perpendicular normal reaction. Part B. Find the magnitude of the resultant force acting on the ramp at A. 9 marks. Alright, So, what is the ramp trying to do? It's trying to fall down through the floor and to the left. So, at A, there are two forces not letting that happen. So, we have the normal reaction to the floor, so let's call that N. And we have friction pushing back to the right. So, what we are trying to find is the force acting up and to the right. So, let's call that X. So, we want to find X. To do that, we're going to need to find N and friction. So, how are we going to do that? Well, we know that in terms of moments, the weight of an object acts down through its centre. So, there is a point 4 meters long where the weight is acting down. So, hopefully this will work. Let's say that this point here. Now the weight was 20 kilograms, so this is 20 G. Now, we also know that this is going to have a perpendicular component and a parallel component. So, just like the last question, we need to find what those two are. So, this angle is theta. So, this time, tan theta is 7/24. So, there's a right angled triangle. With an opposite of 7 and adjacent of 24. Now, using Pythagoras on that, we can get the hypotenuse as, well, that's nice, 25. Now, from that, we get sine theta is 7/25. Now I'm going to turn that into a decimal, so that's 0.28. And cos theta is 24/25, which is 0.96. Alright, so that then gives us our perpendicular component as, so it's 20g times cos theta, so that's 19.2g, and then our parallel component is 20g times sine theta, and that's 5.6g. Alright, so that's the weight acting through the centre of the rod. Now, the other point of interest we have is at C. Now, there's no friction, so the only thing going on here is a normal reaction. So let's call that R. Alright, so let's think about anything we can find now. So, we know that the rod is in equilibrium, so any moments are in equilibrium. So, that tells us then that, so we have two moments. We have the one from the centre and one at R. So, sorry, one at C. So, taking A as the pivot point, the moments are, remember it's the distance from the pivot to the point times the perpendicular force. So, the moment from the centre of the ramp is 4 times 19.2 g. So, I'm going to use g as 9.8. Now we know that that moment must be equal to the one at C, which is 5n. Now, from that we get n is 150.5 newtons. Alright, now that may not seem useful yet. Alright, so the moment through the centre of the rod is 4 times 19.2 g. Now, I'm going to use g as 9.8. Now, we know that that moment must be the same as the moment at C, and that is just going to be 5r. Now, from that, we get that R is 150.5. Alright, now that may not seem important yet, but we can split R into its vertical and horizontal components. Alright, there we go. Alright, so then as a vertical component, and a horizontal component pushing to the left. Now, the angle at the bottom is theta. So, the vertical component is r cos theta. And the horizontal component is r sine theta. So, this is important because we have a vertical component at A and a horizontal component to the right. So now we can start to fill in the puzzle. So we know the ramp is not moving left or right. So that means that friction is the same as r sine theta. So that's 150.5 times 0.28. See what that gives us. So that gives us friction as 42.1. Now, we also know that the vertical forces must be in equilibrium, so we have 2 working up, which is N add r cos theta, and then 1 acting down, which is the weight, so 20 G. So N is 20 G minus r cos theta. Now that gives us that N is 51.5. Nearly there. So now we want X, which is the magnitude of N and friction. So X is a root 41.2 squared add 51.5 squared and that will finally give us that X is 66.5 newtons. Okay, the final part. Now we are assuming that the centre of mass is closer to A than B, and we want to explain what effect this would have on the normal reaction at C. So essentially then, it's now a lighter where it sits on the barrel, which means the barrel needs to give a smaller normal reaction to stop the wrap falling through the barrel, so the normal reaction would decrease. Number 5. 2 points A and B lie 50 meters apart on horizontal ground. At time t is 0, 2 small balls P and Q are projected in the vertical plane containing A, B. Ball P is projected with an initial speed of 20 meters per second at an angle of 30 degrees to A, B. Ball Q is projected with initial speed u meters per second at an angle of theta to B, A. At time t equals 2, the balls collide. Until they collide, the balls are modelled as particles moving freely under gravity. Part A wants us to find the velocity of P at the instant before the balls collide. Alright. So, here's what's going on when P is fired. So, its velocity has vertical and horizontal components. Now the vertical is 20 sine 30. Which is nice, that's 10. And the horizontal is 20 cos 30. So that's 20 times root 3 over 2, so that's 10 root 3. Alright. Now, we know it's moving freely, so we are assuming no horizontal resistant forces. So, we know horizontally U is 10 root 3. Now that is also going to be its final horizontal velocity. Alright, now vertically, so uy we know that's 10. Now, to find Vy, we're going to need suvat. So we're going to use V is U and A T. So Vy is 10. Add 2 times minus 9.8. So minus 2 times 9.8. Now that gives us minus 9.6. So that tells us that when t is 2, p is moving down and to the right. So the vertical component is minus 9.6 and the horizontal is 10 root 3. Now the speed is the size of this vector. So the speed is the square root of 9.6 squared add 3 root 10 squared, which is 10 root 3 squared, which is 300. And that gives us 19.8 meters per second. So that's its speed. Now we need to work out what angle it is to A, B, or the horizontal. So let's call that angle N. Now we know tan N would be 9.6 over 10 root 3. So that tells us N is 29 degrees. So its velocity is 19.8 meters per second. At 29 degrees to the horizontal. He wants us to find the values of theta and u. Alright, so now that we know things about P, we always knew things about P, we can work out where the collision happens. So when T is 2, for P we know its displacement. Horizontally is its horizontal speed times 2. So 10 root 3 times 2. Now that gives us 34.6 meters. And the horizontal, so for that we're going to use ut add 1/2 at squared, so that's 20 minus 1/2 times 9.8 times 4. So that's minus 19.6. So that's 0.4 meters. Alright. Now, for Q, we know our initial speed is u, the angle is theta, so then our vertical is u sine theta, and your horizontal is u cos theta. Alright, now, what else do we know? We know that A and B are 50 meters apart. Now we know the collision happened 34.6 meters from A, so that's 15.4 meters from B. So we want our horizontal displacement to be 15.4. We know our initial is u cos theta. We know the final will be the same. We know acceleration is 0. And we know t is 2. Alright, now let's do y2. So, we know we want vertical displacement to be 0.4. Our initial is u sine theta. We don't know the final. We know that A is minus 9.8. And again, we know T is 2. Alright, so what clever things can we do here? What we can do for both is use S is a ut and 1/2 at squared. So horizontally, we're going to get 15.4 is equal to 2u cos theta. Horizontal acceleration is 0. And then vertically, we know our displacement is 0.4. So that's 2u sine theta. add 1/2 times minus 9.8 times 2 squared. So that's minus 19.6. So from that one, we get 20 is 2u sine theta. And now the magic happens, because we can now do 2u sine theta divided by 2u cos theta, and that is going to give us tan theta as 20 over 15.4. So theta is the inverse tan of that, and that gives us theta is 52.4 degrees. Alright, now we can use 15.4 is 2u cos theta to find u. So if we divide away the 2, we get 7.7 is u cos 52.4. So u is 7.7 divided by cos 52.4. And that gives us 12.6 meters per second. Final question. State one limitation of the model other than air resistance which could affect the accuracy of our answer. Alright, first up, wind and air resistance are not the same thing, so if it's outside, it's probably going to be windy or even raining, so that would mess things up. Or we could say balls might be spinning, which is going to make them move differently, or we've modelled them as particles. They're not, they have dimensions, so that will also affect things. Okay then guys, that's the end of that one. I really hope it's helped. Please subscribe to the channel if so. Good luck in your exams. Take it easy. Take care.